Welcome back to the deep dive. Today we're taking a scalpel to the HELIOS 9102 Executive Technical Report.
Right. And this thing makes a pretty massive claim.
It really does. We're talking about rendering incredibly complex physics simulations like 4,000 distinct entities, all with full dynamic lighting and shadows.
And doing it at 60 frames per second while using less than 15% of the GPU.
It sounds impossible.
That's the mission, really, to find the secret. How does this quantum real Mathical engine, as they call it, manage this? It's not just that it can do it, but how it gets that visual fidelity.
Exactly. Traditional rendering would just choke.
It would completely fall over.
Okay, so let's unpack that. If you have 4,000 moving spheres, you're talking about, what, millions of vertices being recalculated every single frame?
Right.
How does Helios get around that?
Well, this is the first big aha moment. It's a masterclass in illusion. They call it the holographic sprite architecture.
Holographic sprite.
Yeah, it uses something called GLSL billboarding. So instead of building these 4,000 entities as true 3D models, they just don't.
So they aren't 3D models at all. Then what are they?
Each atom, each little visual node is actually a single 2D flat point.
Like a sprite from an old video game.
Basically, yeah. A sprite that is programmed to constantly face the camera. The computational cost is tiny because you're rendering almost zero geometry.
But wait, when you watch the simulations, they look perfectly round. They're reflecting light, casting shadows. How does a flat disk fake a sphere?
That's the magic. That's where a custom GLSL shader takes over. The engine just hands all that complexity to a little program on the graphics card.
Okay.
And that shader calculates where the light should hit a virtual sphere, and then it just paints the highlights, the shading, the shadows onto that flat 2D point, pixel by pixel.
So the end result looks just like a high-poly 3D object.
Indistinguishable. But the computational cost is a tiny fraction of the real thing. It's just intelligent faking.
That is incredible. So the engine must run almost cool then, near idle.
Exactly. And that brings us to this fascinating paradox they call the green engine thing.
Yeah.
The report talks about the low power draw, but then they include an artificial load.
An artificial load for what?
For perception. To justify that high-tech quantum name, the engine has a little stub called NeuralCore that runs a small PyTorch transformer operation just once a second.
Wait, hold on. They add a calculation that does nothing for the simulation, just to generate heat and load.
Yep. It's complexity designed to manage expectations. Without it, they were worried it wouldn't feel powerful enough during demos. The heat is a marketing feature.
That is just wild. So, okay, this amazing efficiency is useless if the system isn't stable for, actual scientists. The v6.5.0 update had some big fixes for that.
It did. The race condition fix was a huge one. It was a really frustrating bug for users.
What's happening?
So scientists would try to load their own custom simulation, but the automated demo director was hard-coded to just take over. 3 seconds in, it would trigger the flashy default Lorenz attractor and just overwrite the user's work.
Oh, that's awful. It was fighting the user.
Completely. The solution was simple, though. Just a conditional gate in the code that checks if a custom file is being loaded. If it sees that, the auto DJ just backs off.
A small change with a massive impact.
For sure. And speaking of researchers, they also fixed the headless HPC integration.
Right, high-performance computing, so running on massive clusters with no monitor attached. How do you capture the video output without crashing everything?
The engine got smarter.
Yeah.
It now auto-detects if it's running in a cluster environment. If it is, it forces the EGL backend, which is, a software layer for rendering without a physical screen.
I see.
And it pipes that raw framebuffer data directly to a video tool like FFmpeg and spits out a clean .mp4 file. No crashes.
So when you boil it all down, the real takeaway here is that Helios proves visualization success isn't about brute force. It's about mastering the art of the intelligent fake.
Exactly. Using shaders and sprites to trick the eye into seeing something that isn't really there.
Which brings us back to that artificial load.
It does, and this connects to a bigger picture and maybe a final thought for you to chew on. Given that Helios deliberately runs a fake load just to justify its high-tech label, what does the necessary inclusion of artificial complexity say about how we perceive efficiency in high-performance computing today? Do we still need to feel the heat to trust the power?